All right, so we're looking here at moment of inertia. We've been doing this for a while now. There are a couple different kinds of moment of inertia. What we're doing is the area moment of inertia. In physics and dynamics, you probably do something called the mass moment of inertia, which it's related, but it's not the same thing. So keep that in mind. All right, now what moment of inertia is a number that essentially tells you how a shape will respond when you bend it. It's got nothing to do with the material you make the object out of. It has everything to do with the shape. And the basic moment of inertia formula is based on an axis. You always take moment of inertia about an axis. And it's the sum, which, you know, is often expressed as an integral there, of an area times the distance from the axis to the area squared. And then you break the shape up into a bunch of little areas and sum those things up. Okay. And what this quantity does, again, is express how well a shape would essentially resist bending. Now, when you look at a beam, you take the moment of inertia about the neutral axis. Now, you find the neutral axis on the cross-section of the shape. It goes through the centroid of the shape. And then you run the neutral axis down the length of the beam. Okay, that's kind of how that works. So you find it on the cross section though, then you run it down the length of the beam. And as a beam bends, on one side of the neutral axis you have compression, the other side will be tension. The neutral axis is called neutral because it's that line that is in either tension or compression. It's the boundary between the two. Right, common shapes that we deal with that have a good ratio of area, which would really relate to the amount of material you're making the shape out of, to high moment of inertia or I-beams. Okay, so we use a lot of I-beams in structural engineering. Other shapes are T's, channels, pipes, and tubes. Those are common things that we make beams and columns out of. They all have high moments of inertia and use the material efficiently. Is kind of the idea. So you want a high moment of inertia for a low amount of material. Lower material gets you less cost, it gets you less weight. Okay. So there are just some common structural shapes used in different applications. There you see I-beams, double T's, tubes, things like that. Okay, there's a common material used for floor joists in your house these days. Again, it's an I-beam, is what it is. Kind of an odd-looking I-beam, but it's an I-beam. When you call out I-beams, you start with the shape. That's called out by letter. W is the common one these days for wide flange beams. Then you've got the nominal approximate depth and then the weight per foot in pounds. That's how you call out I-beams. So there's W's, there's I's, there's M's, and then there's HP's. Those are the common I-beam types. I'm sorry, the I's are actually S's, aren't they? I guess they're S, yeah, for standard. All right, and then we can calculate this idea of moment of inertia. The one thing, you know, when you're doing practical everyday engineering, you're going to use an algebraic approach. You're going to break the object up into a bunch of smaller shapes, usually rectangles for most of the standard shapes we use. It could be circles as well. And then you use what's called the transfer axis theorem. Because when you have composite shapes, which we often do, like a T-beam, the centroid of the shape, which is what the table will give you the value when you calculate the moment of inertia about the centroid, is not on the neutral axis typically when you've got composite shapes. So for each one of those shapes, you're going to have to add in a transfer axis term, which is A, the area of the shape, times D, the offset distance squared. So that's the basic way you find the moment of inertia about an axis not equal to its centroid. It's I bar, which is the centroidal moment of inertia, plus AD squared. All right, now one other thing maybe I should mention while I'm thinking about it is with the moment of inertia, it has to do with the nomenclature, the way you name things. The X here means take the moment of inertia about the x-axis, okay? which means a lot of the measuring you're doing for the offset distances are actually in the y direction, okay? But you're taking the moment of inertia about the x-axis. Now for a centroid, if you say x bar, what that means is measure in the x direction. Okay. So these things have kind of different ways of naming them. The centroid is named after the direction you measure, whereas the moment of inertia is named after the axis you take it about. Normally you measure perpendicular to the axis. So I sub x, the measurements are done in the y direction, okay? Whereas x bar, the measurements are done in the x direction. Keep that straight, okay? So because they're different, and you would want to be sure we know which, how to, what the names mean for a centroid moment of inertia, okay? All right, so let's look at an example of this. So let's find I bar sub x for this T-beam. I'm on 740, I think is where I'm at. So I have a T-beam. Now the first thing I want to do is figure out where the neutral axis is. So step one, find the neutral axis, okay? Now we're finding I bar x, so that means we want to find y bar. Okay, that's what we want to do. So that's the first thing to do. Now I like doing these things in tables, so I've got tables set up for you there. Let's just find y bar in the simplest way, so let's break it up into A and B. Okay, so let's start by finding the area of A and the area of B, and also finding the distance to the centroids of those from a convenient location, generally speaking, the base of the entire beam. So what's the distance up to the centroid of B? What's the distance for the centroid of A? And what are the areas of the two shapes? So I like to get this stuff kind of figured out first and get this kind of, put on the side so I can use it. I might need this a couple of different times. So why don't you knock those out real quick. Get the area of A, the area of B. You've got the dimensions of the beam on the left. And then find the distances from the base to the centroid. Okay, so the area of the top's 24 square inches, 8 by 3. On the bottom it's 20. And then the distances are half of 5. And then 5 plus half of 3, 3 over 2. Okay, is that all right? Now, I like drawing pictures, okay? Sometimes people have a habit sometimes of forgetting to put the offsets. So they'll use 3 over 2 for the height of A, that centroid of A, which is not correct. Okay, you got to remember to add the 5 in. And see, that's why I like making sketches. I want to make it visual and common sense. My operative assumption is I'm not really particularly bright, okay? So I need all these crutches to help prevent me from making mistakes, okay? And what that does, it really helps me because I make less mistakes, okay? So, if I just do all these things, if I develop these good habits, I don't make the mistakes, and then I don't have bosses getting upset at me. I'm not losing the company money. I don't have contractors telling me I set a grade stake wrong when I'm surveying, all this stuff, you know. It just makes life better, okay? And, you know what I'm saying. I say this a lot, but you're gonna work someday, you know. Get these habits going now. The price is a lot less to pay now to develop the habits than it would be when you start working, you know. It's just a good thing to do, right? Right? So there we go. Okay, so now we got that information. Now we just fill in the table, right? I like the table again because it organizes the information. I just, less mistakes when I'm organized. So we got the areas, we got the Y bars, we just fill in the table, then we run the multiplications, add the stuff up, and figure out Y bar, right? I mean, that's about it. So now what I'm doing here is I'm compartmentalizing my work. I'm getting the areas and the Y bars first. I get that done, then I can fill in the table. When I do both at once, I start kind of jumping back and forth. I'm more prone to make an error, you know. That's why I'm doing it this way. Okay. So just fill in the table. You got the areas, you got the Y bars, and then you can just multiply the stuff out. Now, you know, you'll see this on an exam sometime, I'm sure, because we're doing this beam design stuff. You know, you'll have to make your own tables, so, you know, be sure to do that. So we got 24 and 6.5 for A. We just multiply them together, we get 156. Do the same thing for B. 20 and 2.5 gets you 50. Then add up the column on the left and the column on the right and divide it out. And we get 4.68. All right. And then last little step here after I've done that is I plot it up and I look at it. You know, if that sketch is about to scale, if that's the centroid, I look at that. I say if I cut that out of, you know, a piece of wood or something, a board, and turned it horizontal and balanced it on my finger, would that balance there? You know, that's what should happen at the centroid. That looks about right, okay? Now, I think I must tell these stories, but I worked for a company, we did a lot of surveying, we were locating a bridge piling. I was walking into the meeting with the coordinates that the person on the computer had just generated, and the clients are there, and there just happened to be a map on the wall. So as I was walking in, I looked at that latitude and longitude on the map, and we were going to put that bridge piling in Oregon, and the thing belonged in Alaska. There was just something wrong with that, you know. So I was a little late to that meeting, but I got it turned around and got it straightened out, you know. So that common sense kind of check, again, that's a good thing to do, all right? All right, so there we go. So now we got the neutral axis. Now we want to find the moment of inertia about the neutral axis. So what we do is we fill out first the I sub x, okay? And, you know, I don't really like how I have this notation on this. I didn't really notice this before, but I think we want to rearrange this a little bit, because what we're doing here is we're using the transfer axis theorem, and the transfer axis theorem tells us that I sub x is equal to I bar sub x plus AB squared. So let's get rid of the bar on that. Let's just call that I sub x, because that's what I need to do there. And let's put a bar over that one. Okay? All right, now the centroidal moment of inertia for a rectangle is the base times the height cubed over 3. So for A, I've got, what, a height of, well, let's see, I got a base of 8. 2, 4, and 2 makes 8. Height of 3. 8 times 3 cubed over 12 gets me 18. The area is 24. Okay, so the BH cubed over 12 gets me 18. The area is 24. Now, the one little bit on this is getting these offset distances. So what I've got there is I've got the distance from the neutral axis to the centroid of the shape that I'm working with. I'm working with that rectangle on the top. So it's 6.5 minus 4.68. 4.68 is the neutral axis location. 6.5 is where the centroid of A is. The difference is positive 1.82. So what I do, I take the area, 24, times the offset distance, quantity squared, that's 79.34. Okay. So that's the transfer axis term, the AD squared. I add that to the BH cubed over 12, and that will get me the total moment of inertia of A about the neutral axis. That's what that gets me. So that's how I would do that. So how about doing the same thing for B there? See if we can work that out. So we want I bar x, which is BH cubed over 12, the area, which you've got already, the distance, which would be from the neutral axis to the centroid of B. Then you go AD squared and add it to the BH cubed over 12. Now, when you're doing moment of inertia, there's no negative values, okay? Some of those offset distances are negative, but you square them so the negative goes away. So unless you're doing cutouts, there should not be negative values on moment of inertia. Whether the shape is above or below the axis doesn't matter. Everybody doing all right on that? Do something on that? So BH cubed over 12, straightforward enough, I think. The area we've already got, get that distance from the neutral axis to the centroid. It's going to be down, that's what it's going to be. From the neutral axis of the beam. So the neutral axis of the beam is right there. You want to measure down to the centroid of shape B, like that. That's your distance, the offset. Now that's going to be negative in this case, but you square it, so the negative goes away anyway. So again, it's not a big issue. Some people don't even bother with the sign on D because you're going to square it, so it doesn't matter. Okay. And then you're going to multiply that by the area, and that's your transfer axis piece. So I got 41.67 for BH cubed over 12, 20 for the area. It's 2.5. That's where that centroid of B is. The neutral axis is at 4.68, so the difference is negative 2.18. People often, again, they don't bother with the sign so much because you're going to square it anyway. Take the square of that times 20, you get 95.21. Add it to the 41.67, you get 136.87. Add that to the 97.34, you get basically 234. The units on this are rather odd. They're inches to the 4 is what they are. Okay. So the higher I sub x, the more that beam shape would resist bending when you load it up. And it bends about that long neutral axis down the length of the beam. Okay. So we're going through all this stuff so we can design beams. We're going to look at moment and shear in the beams and the types of stresses that those actions create. The neutral axis location matters in this. The moment of inertia matters. There's one other thing that matters, and that's the shear in the moment. And some of the beam dimensions can matter too, depending on how you're analyzing. So we good with all this stuff? All right.